wait a few seconds while people...
Thank you. All right, thank you. I have a much narrower talk than the two that we've seen this morning. Very grandiose and high-minded concepts this morning. So back to something narrower and simpler. I'll be talking on the separability in the many worlds theory, and where this is located is within the debate about non-locality. And it was interesting last night at the panel discussion that at least a couple of the panelists felt like non-locality was one of the biggest differentiation features between quantum physics and classical mechanics. So just to give the background for anybody that isn't as familiar with the philosophical literature, but the philosophical literature really distinguishes non-locality, two separate principles, a violation of either one giving us non-locality. So the principle of local action, Einstein's original principle, roughly if A and B are spatially distant things, then an external influence on A will have no immediate effect on B. Now I think it's fairly well, I think there's a fair consensus that in Everettian quantum mechanics, at least, there's no violation of the principle of local action. But I think Don Howard was the first to point out that there's a second sort of principle, and Einstein made references which could be interpreted as this principle. I think Don also suggested that he sometimes maybe confused the two, but his point was that there's this second principle, which he called the principle of separability, not stated in this way. I've paraphrased it in a sense. But in essence, the principle of separability is that the state of a compound system will be completely determined by the state of its subsystems. That's the essential. That's probably all we need for the discussion to come. So that's the background. So my claim will be that in the many worlds interpretation, that non-separable relations are external relations between intrinsic properties. I'll unpack what that means a little bit in a second. But what I'm claiming is essentially that it's akin to classical relations, that in fact, non-locality is not the bugbear that we might have thought it was for quantum physics, that perhaps it's also a bugbear for classical theories as well. Okay, how we'll get there. So first of all, we'll understand how non-separability should be understood in deterministic theories generally. So, it's historically framed in terms of single world theories and probabilistic theories. So we'll try to understand what it means in a deterministic theory. And then we'll try to show that there are both classical and quantum relations that satisfy this generalization. And then I'll quickly defend against two objections. So the way it's conventionally put in any standard first year quantum physics textbook, that the separability, that the state of a joint system, of a compound system AB, is considered separable if and only if it can be written as the tensor product of the state of A and the state of B separately. Standard textbook definition so far. In single world quantum theory, what this means is that the probability of any joint result for A and B has to factorize into the probability of the result for A and the result for B. That's how we interpret it. So, and you can understand in classical theories why this seems mysterious, because classical probability doesn't work that way. In a classical probability, if we have two sort of systems that are at a distance, then any statistics that we get will factorize. A joint result will, the probability of a joint result will factorize into the probability of the two separate results. So hence the mystery. So, but if we take that translation and apply it literally into deterministic theories, and the many worlds theory is one of those, we run into problems, conceptual problems, because if we want to think about it as probabilities, although we can make interpretations for how we should interpret probability in the many worlds theory, but like genuine probabilities, we genuinely have the joint result occurring with a probability of 1 or 0. And we have genuinely the probability of A occurring with 1 or 0 and B with 1 or 0. So we run in, when we try this literal translation, we run into this problem that everything factorizes because the two joint states have a probability of 1, the two individual states have a probability of 1 and the joint result also has a probability of 1, so they do factorize. So what we need is to understand what we mean by this concept of separability. So to go back to Don Howard's suggestion and others who've synthesized it since, we'll remind ourselves that this principle of separability is a nice way to put it, that what we're worried about is that we want the state of the compound system to be completely determined by the states of the subsystems. So there's nothing left. If you know the state of A and the state of B, there's nothing left to know about the state of A and B. So that's apparently the mystery of quantum mechanics. So, but the question is, according to that definition, are joint states really separable in general relativity? So take as an example, we have two laboratories. We have the laboratory A frame and the laboratory B frame. We look at those little the little patch of space-time that each one is in. So we take each space-time region U, we map to some sort of Euclidean coordinate system through phi A and phi B, and we have these two vectors VA and VB. So we have, initially, if we take the two patches separately, we have this disjoint state. We can think of it just as a union of the two states, and we don't have any direct way to compare the two. Again, in general relativity, the warm-up, again, the usual textbook demonstration, we could think of this on a spherical surface, for example. So if we take the white vector and we parallel transport it over to the yellow vector, then we can compare them. Then they'll overlap, and then we can compare whether the two are, in fact, parallel or anti-parallel. And the path that we take matters. So in one case, in this standard example, you go east-west, the other north-south, and in one case you end up with an anti-parallel comparison, and the other you end up with a parallel comparison. So the transport path matters, and the metric matters as well. And this is a simple metric, but of course in general relativity we have these arbitrarily curved spacetimes. So we have two vectors in two different locations, and we can travel by one path and compare them. We can travel by another path and compare them, and the metric will change from point to point. So, we need this sort of summary map, this parallel transport map that takes us from one to the other so that we can compare them. So the joint state, if we want to propose a joint state, we'll have this local state for VA, this local state for VB, and we'll have this parallel transport map between them, this third piece of information. So, and if we want it to be globally complete, we'd take every space-time path, and then we'd have the absolute complete relation at some foliation in time, for example, of every possible path. Okay, so what that appears to suggest, the joint state is in part determined by the path and its metric, so it's not completely determined by the states of the subsystems. And if so, according to our definition, is non-separable. Okay, two objections, which I'll quickly deal with. But first of all, the being parallel is not an intrinsic property of the subsystems. We'll deal with that in a sec. And then second, that the local states of GR aren't missing anything, but the local states of quantum mechanics are. So I'll explain those objections in more detail. So objection one, being parallel in general relativity isn't an intrinsic property of the composite system. It's in part determined by features of the outside world. And what we might want to say is that by contrast, the entanglement relation is entirely intrinsic. We don't need the outside, we don't need a space-time path, we don't need an outside metric, we just need the two systems and we've got everything. So we might want to modify our principle and say the principle of separability should read the intrinsic state of a compound system is completely determined by the intrinsic states of the subsystems. And I think that's probably reasonable, but what we really want to know then is what we mean by the entanglement relation being intrinsic. So we should really want to ask, is it intrinsic, and by what do we mean when we say that? Okay, so diagrammatically we might think of the entanglement relation in this sort of way. We have two particles, spin singlet state, and they're not in any one determinate state on their own. So the local pictures we see of this sort of maximally uncertain. We don't know whether they're up, down, left, right. We can measure them in all sorts of different ways, and we don't know what the outcome will be. And in many world theory, we say, in fact, they'll separate. So if we have, say, this dark blue spin up and this dashed blue spin down, what we're thinking is there's going to be two worlds ultimately. We're going to have one as the spin up and one as the spin down. And if we measure particle B in the same basis, this sort of blue line up and down, we'll get the completely opposite result. So if we get the dark blue up, we'll get the dark blue down for particle B. So that's sort of conceptually how we might think of that entanglement relation. It's more complicated, of course, for off-kilter measurements, but okay. So, and just out of respect for the other Bell states, this setup, is equally compatible. We could think that of rotating, say, particle B into all sorts of positions, and we'll get all of the other Bell states. Is an example of 4, but we get this correlation just through the local rotations of one of or the other of the particles once we've got this spin singlet state. Okay, so measurement in the many worlds interpretation. So if we take our particle, put it through, say, a Stern-Gerlach device with a particular measurement setting, in this case up-down, we'll split into an up and a down world, put it in-out, we'll get an in result and an out result. So far so straightforward. So in the combination where we have the two entangled particles, again, we're just thinking diagrammatically here, and I'll explain in a minute why we're using this to understand it. We have the two entangled particles. They go through a particular measurement angle, and that measurement angle now determines which world they end up in. And we've got 2 worlds here, but we could easily have 4 worlds or more worlds if we had more entangled particles. So in this case, the joint state describes the local states and how they would compare if measured. So the measurement then implies splitting into worlds. The split into worlds is determined in part by the measurement settings. And the possible measurement paths themselves, however, aren't intrinsic features of the subsystems. So the relation we have is tied to the measurement settings and all of the possible measurement settings that we might possibly have made. So in essence, it's tied to some external feature of the world, some external way of doing things that is not necessarily a feature of the systems themselves. So objection 2, that local states in classical theories aren't missing anything. So this would be the objection that a local state in GR tells you everything you actually need to know about the local system, whereas a local state in quantum mechanics is somehow taking a full state, chopping it in half, and giving us some sort of reduced picture, some reduced story. But I think when we look at the way that it's presented, we see a really similar picture emerging between the two. So in classical terms, we can have disjoint states. We can have 2 disjoint patches of space-time that we just treat as though there's no, without any comparison, without any overlap. And alternatively, we can take those 2 states, we can add a third term, which tells us the parallel transport path and the metric that we need to use to come up with the final joint state, which is 2 patches of space-time, some new phi, which is the mapping which is determined after we apply that parallel transport map to get some sort of unified picture, and the 2 vectors themselves. So we have one joint state with all of this information built into it. And similarly, in quantum mechanics, we have this disjoint state. We have rho A and rho B being the reduced density matrices of the 2 particles. And we can also describe it with the joint state, which is rho A, rho B, and some E, the entanglement relation, which we can use to map the A's and the B's, the components of A to the components of B. And with that information, we can have row A, B. Now, normally we would go the other way around. Normally we would start with row A, B and decompose it into row A and row B. I don't think anybody usually tries to actually just get the entanglement relation separately, but I'd be interested to hear whether anybody does that. But so therefore I don't have a very good symbol for it, and I've only used E. But normally we go backwards, whereas in general relativity we normally go forwards. So it's perhaps just a different way, a different thought process in the two theories. Okay, so in summary, to wrap up, in both general relativity and quantum mechanics, when we're talking about deterministic quantum mechanics, and many worlds in particular, the subsystem states can each be described with only local information. A joint state describes not only the local states, but also how they would compare if they were brought together. The comparison depends on external paths, in one case a space-time path and the other a measurement path, if we like. Joint states aren't completely determined by the states of their subsystems, and so, by the definitions that we started with earlier, both are, in that sense, non-separable. Now, alternatively, before I put the conclusion in, I'm also open to the possibility that we just want to call them both separable. That's also an option. But I guess my point is they're of a similar nature. And therefore that they are just as mysterious as each other. If the joint states of quantum mechanics are mysterious because there's entanglement, then the joint states of general relativity are also mysterious. Thank you very much.
I'm not sure I exactly understand. If I know everything about other systems,
Yes.
then in classical case, adding this local description of my particles, local description, completes the picture, and then I know everything. In quantum case, I know everything about all systems, and then I have a local description of my two particles. I don't know everything.
Yeah.
So quantum is non-separable, and classical is separable.
So I suppose my argument is that in the classical case, you don't know everything. There's something that you don't know. The thing that you don't know is how Alice's vector will compare with Bob's vector. You don't know that. You know what Alice's vector is according to your own local information, but you don't know what it will be according to Bob's information. So we need to take that vector over to Bob's position.
If I know the distribution of all the other masses and everything, so I know for every pass how they will compare.
Yes.
So
that's a great point.
This is the whole information. Of course, it's counterfactual. If I'll do one measurement, I'll get twice. Do another one, I'll get another outcome. So if I know the whole geometry, the whole masses, all mass distribution, then I know, and then for every pass, I know the outcome of experiment.
Yes.
The same thing, this is not true in quantum mechanics. I know everything about everything, and then I consider all possible experiments. And but about my two particles, I have only local description. This is not enough to make to know what will be the outcome of the measurement.
Yeah, no, and it's a great point. And I think it's probably the thing that's in the back of most people's heads. The piece of extra information, though, that you introduced in the classical case was that I know the mass distribution of everything. So that's an external piece of information. If I know the sort of global metric of I solve the field equations of the universe, I know something more than just what Alice knows. I know something about the bigger universe. And if we were doing that in quantum mechanics, we would take this sort of global Everettian outside the box picture where we knew everything. So we would know what the relations between Bob and Alice were. So
knew everything about other things and don't know about these two particles. I don't. So this is the difference. In classical case, I know everything about the other parts, add local description of my two particles, and I know everything. This is not the case in quantum. This is why there is nonseparability in quantum mechanics. But I should give to us.
Thank you. Thank you.
I'm just wondering how crucial the use of general relativity is to this setup. I mean, it feels like even in a flat space-time, you can still say, well, look, the intrinsic properties of system 1, and the intrinsic properties of
Yeah.
system 2 then specify the spatiotemporal relations between them.
Yeah, absolutely. No, and I only use general relativity because it's a really clear example. But you're absolutely right. I mean, you still need to know, and I actually have another slide. Interestingly, David Lewis, I stumbled across this definition just recently. So if we recast the principle of separability in terms of supervenience, which I avoided because I talked to some physicists and they berated me endlessly about the use of the word supervene. So, but if we go back to it, we would say the state of a compound system will supervene on the state of its subsystems. And Lewis, in fact, defines an external relation by which he's talking about spatial separation in particular, as a relation that does not supervene on the intrinsic properties of its relator, but does supervene on the intrinsic properties of their composite. So yeah, I think you're absolutely right. I think it's not critical to think of this in terms of general relativity only. Yeah. So great, thank you.
So I think, sorry. Here.
Oh, sorry.
Look, you have a formal definition of non-separability, but if you're applying it to GR, I just don't think it's the right definition. I don't think the definition that Lewis gives is the right one. It's not the one that's used there. The one that's used there is very clear. I have a manifold, and I cover it however I want with a set of charts, with an atlas of charts, where the charts have to be open, which means they overlap, right? And if I specify the local situation in each member of in each chart, and I've got the overlap relations where they overlap, then I have specified the global situation.
Yes.
Everything is specified about the space-time geometry.
Yes.
To that extent, the metaphysics, as it were, of GR is completely local and separable, right? It's all local beables in Bell's sense.
Yeah.
That's what's not true.
Well,
right? It's not like you can fill in by, as it were, a set of local, overlapping local objects between Alice and Bob and recover from the density matrices. I give you, to follow your analysis, I would cover the thing with a set of local charts. I give you a density matrix at each chart. That will not settle the global state.
So, and it's a great point, and somebody else raised this sort of question earlier, and so I guess the missing piece of information in the entanglement case is this overlap. You know, what is this overlap thing? You know, what piece of overlapping information would we have? So if we have all of these charts in GR, we have all this overlap.
Hi, thanks for the talk.
Thank you.
I'll have to grant you that joint states are not completely determined by the states of their subsystems, and so are non-separable. If we take states to be either wave function or reduced density matrices. There's just no way to, it's well known. But this has no bearing on the non-separability of quantum theory. Quantum theory is entirely separable because if you jump in the Heisenberg picture of things, you can define what are states, but I will not use the word states. They're descriptors, and then joint descriptors are completely determined by the descriptors of their subsystems, and so are completely separable. So
look, I won't quibble over whether we want to call them both separable or both non-separable. I mean, I feel like, you know, if
no, that's not my point. No, they are, wave function is non-separable. I'm not trying to find a cute definition that then allows us to make sense of separable. I'm taking your first definition of separable. And wave function is not separable. But Heisenberg picture descriptors are completely separable. And so...
But so we dissolve the mystery of non-locality if we feel that those descriptors are separable. We have a separable theory then.
So yeah, if I want to make it a question, then it would be sort of, knowing this, why are we still doing all these things with the object that we know is not separable? So, I mean, you know, like you can always start from a separable theory and define crazy quantities and say, oh, these quantities are not separable.
Yeah.
So the theory is not separable. No, you need to have one framework
yeah.
in which it's separable, and you know that the theory is separable.
Yeah, I don't think I'm going to try to defend the version where there is something mysterious going on. I'm not going to, try to defend that alternative point of view. Yeah.
Okay. Then maybe that's also a reason why we don't reach consensus. If we insist too much on defending the objects that we've been trained to learn quantum theory with, and we refuse to change our mind even when we're presented with an object that solves the problem, then how can we reach consensus?
Yeah, yeah. Thank you, Paulo. Yeah. I think we're at a consensus. Yeah, I don't think. I think that there are perhaps some people that don't hold that view, and they might not be in the consensus. Those who think that there is something really vastly different, in these non-separable relations. But yeah, I'm not one of those. I'm with you. I'm in the consensus. Yeah. It's just this word non-separability. What do we mean by it? And if we want to take this definition that I gave, joint patches of space-time are non-separable. So if you want to abide by that definition, then you would apply it more broadly than we do apply it at the moment.
Yeah, then I have to disagree with you. I think that it is a problem being non-separable. I think it has clearly caused a lot of confusion. And even in this conference, there were several talks complaining about the non-separability, about the global object, and so on. And also this question about when Bob splits, and Bob doesn't split, but his particle splits. Like what splits on his side when Alice does something? It's just a terrible way of writing out the theory. Yeah. We shouldn't, if there is a way of making it separable, we should never make it non-separable.
Yeah. But if non-separable can just be reduced to a relation, if non-separability are just relations, it's not such a bad thing. If a relation is an external piece of information about how two things will compare, then there are lots of non-separable things. Why are we so worried about it?
Okay, but this is not true either. The entangled state is intrinsic property. It is not dependent on some external measurement path. It's not about measurement.
Yeah, well, and that's where we would disagree. Yeah.
We should talk later.
Yeah.
So I want to begin by strongly endorsing everything, once again, everything Tim said. And but I want to extend it a little bit, because there's actually, it's a little misleading to say, it's a little too quick to say, well, there's no principled way to compare directions at different points of curved space-time because a parallel transport is path dependent. End of story. I'll give you a physical way. You give me any 2 points in space-time and I will give you a principled way to answer any question about relative directions at those 2 points for any path. That will be consistent for any path you take. So at the first point, fix three gyroscopes in spatially orthogonal directions, and now any path you want, just transport those gyroscopes along any path you want. It's called Fermi-Walker transport. Fix the original direction you're interested in. Parallel transport that. Keep track of how it changes with respect to the Fermi-Walker transported gyroscopes. And at the final point, for any path you take, I can tell you exactly what the change was with respect to my original 3 gyroscopic configuration. I can answer any question you want in a principled physical way about different directions at different points of space-time. It's not the only way of doing it, but I claim any question you want to ask, this is a physically principled way of doing it. So I think that the way that GR is separable is even stronger than the way that Tim.
So if you wanted to ask the question, are they parallel or anti-parallel? Could you answer it without knowing the path?
I claim that you would get a consistent answer if you use the comparison with Fermi-Walker transport along any path, whether yeah.
His claim is it depends on the path. You have to choose the path.
Yeah, if all you do is parallel transport, he's right. If you keep track of the difference between parallel transport and Fermi-Walker transport with your three originally chosen gyroscopes, you'll get a consistent answer. Now the answer will depend on what configuration of gyroscopes you pick at the beginning. But I've given you a consistent way to answer the question for any two distant points of spacetime. No, not at all. So it makes a difference which original configuration of gyroscopes you choose, but once you do that and you Fermi-Walker transport those, you'll get the same answer for any path. But you'll get a different answer for initial configurations of the gyroscopes.
Yeah, perhaps we need to pick that up after. Thank you.